How's it going, Sheldon?
Yeah, time.
Yeah. What do you think? After action, we'll start to at least plan out. Let's write the code for that. For the way, for the clients.
This is always MATLAB. Yesterday, but it's not working.
It's not running at all.
I tried to download 2022B, and now the MATLAB doesn't work. So I don't know what happened.
Yeah, that thing's been hanging up. I've noticed that too. We'll figure it out today. But I will send you. Did you already write the code for biisotropy?
No.
Okay. Yeah, I'll send you, or we'll try to figure it out. Yeah, that's right. Yeah, we need to do that. Okay, let's set that up. Make sure we get that going. So it doesn't start the parallel pool at all?
No.
Yeah, that's what I noticed too. All right, we'll fix it. Ready for your prelim or what? Or your quals? Quals, right? Quals. What do you think about the questions? One of them's a little, we haven't gotten to it yet, right? But you should be able to do it.
Question 1.
3?
The DGS?
No. The scattering with the hole in it.
Yeah. Then,
Oh, yeah.
yeah.
We'll get to the point today where you'll be able to solve that.
Oh, good.
But you can find it in the book. Questions are too easy, huh?
Too easy?
Yeah, well, I'm starting to think they're too easy. Yeah, ask him if you need clarification on the question. Do that earlier than later. Okay, I think we got everything set up here. So happy Halloween, everyone. That's the first thing. It's gonna be fun. Hopefully you guys celebrate. It's my favorite holiday. But okay, so let's go ahead and get started. You guys got your grades for your midterms and your homework 4. They were uploaded. If you haven't seen them, go ahead and check it out. Take a look. And let me know if you have any questions or concerns. I will be returning them today, physical copies if you're here. And if you are an online student and you want your physical copy return so you can have some feedback, email me and I will scan it and send it to you. So you get some feedback, all right? There will be a homework 5 that's going to come out today. And I might combine it with homework 6 so you'll have 2 weeks to do it. Maybe, I don't know, don't hold me to that yet. But you'll get a new homework today. And the due date will be on the homework, so you'll see when it's posted, when it's posted, when it's due. At worst case, it'll be due a week from today. And best case, 2 weeks from today, and I'm gonna lump 2 of the homeworks together. All right, be a little easier for you because then there'll be less questions for each chapter. All right, there are no questions on the logistics of the course. We have 9 lectures left and 3 chapters left. So about 3 lectures per chapter, and I think that's pretty good for us, so we can go a little slower. All right, so here we are, lecture 6, auxiliary vector potentials, construction of solutions, and radiation and scattering equations. So here what we're trying to do is we're trying to calculate, so in the beginning of the course, when we did chapter 3 or lecture 3, what we did was we solved the wave equation in cylindrical, rectangular, and spherical coordinates. And first we constructed that wave equation and it ended up being a homogeneous equation, right? Homogeneous wave equation, homogeneous differential equation, meaning the right-hand side was 0. They're differential equations, so they relate the fields or the quantities at neighboring points with respect to some point, right? How it changes neighboring points. So, so you can choose points to solve those differential equations that the sources don't exist. And that's how you get a homogeneous wave equation. In that sense, as we saw, it becomes an eigen equation, and you're really solving for the mode supported by the medium and the geometry. So here we're going to consider a different case. We're going to derive wave equation, which is inhomogeneous, where we do have a source. And now we can solve for fields radiated by source distributions. So if I have a current distribution suspended in space somewhere or on some surface, I want to find what the electromagnetic wave or electromagnetic fields are that are radiated by that current distribution at all points in space, right? And we're going to exploit the concept of linearity or the property of linearity of Maxwell's equations in order to construct what's called a spatial convolution integral and allow us to solve these differential equations, these inhomogeneous differential equations for arbitrary distributions of current. So that's what we're going to do, all right? So this is the exciting lecture. This is where you start to pick up a lot of power in solving problems because, you know, most of it is, so I might have some excitation, and if I'm solving a scattering problem, then I have some geometry, and the main part of the problem is to find this current distribution. How do you do that? There's many ways. We can do it numerically, which we'll do next semester, or you can use a concept called physical optics, which we'll go through in this course. And there's other ways to approximately get the current distribution. For antennas, for example, you know approximately what the form might look like. If you can obtain the current distribution, then you can calculate the fields from it. So that's once you have the current distribution, you have everything, because we're going to learn the machinery today of how to calculate the radiated electric and magnetic fields due to arbitrary current distributions. All right, good. So to do that, remember in the first lecture, or no, that was lecture 3, we derived a, so in spherical coordinates, in rectangular coordinates, we were able to separate the vector PDE into 3 scalar PDEs, and then we worked on solving those. In cylindrical coordinates, we were able to separate the vector PDE into 2 coupled PDEs and 1 uncoupled PDE for the Z direction, Z component. And we ended up solving that one, right? Which restricted ourselves to modes which are TE and TM to Z. Okay. In spherical coordinates, however, we were unable to do the separation. All 3 PDEs remained, scalar PDEs remained coupled. So what we had to do is we resorted to vector potentials. And we derived a homogeneous differential equation, a homogeneous wave equation in the vector potential framework. So we have seen some of this before in lecture 3. All right, but now we're going to derive an inhomogeneous PDE in the vector potential framework. So here, let's look at what we were doing again. So here we have sources, J and M. That's the input to the problem, right? So we're assuming somehow we've obtained these current distributions, which we will using numerical methods or approximate methods. We'll get to that later, right? Next chapter, we'll start looking at ways to approximate J. But assuming we have J as input, how do we calculate E and H, the radiated fields due to that current distribution J and M, right? Well, there's a direct path, which is called the integration path, or we can take an auxiliary path, which involves 2 steps. First, we calculate what's an auxiliary potential, auxiliary quantity called vector potential A or electric vector potential F. And from there, we can calculate E and H directly. So one's an integration, one's a differentiation. And we'll look at that in detail, all right? The integration path is a lot more difficult for inhomogeneous differential equations, inhomogeneous wave equations. So, all right, let's look at what's difficult about path one. So let's say we have sources J and M. We want to find what E and H are radiated by them. So we have this integration path. We call it direct path, right? We start with Maxwell's equations. We have the curl of E minus J omega mu H, curl of H, J omega epsilon E plus J. We know our solution is in here, right? In these two equations, because everything that governs electric and magnetic phenomena are described by these and the others, right? Okay, so first thing we do the same trick. We uncouple these. These are coupled differential equations. So we take the curl of the first equation and we substitute in the second. The curl of E minus J omega mu curl of H. We know what the curl of H is from Ampere's law. We substitute that in and we keep the J this time, right? So all terms are there. We have omega squared mu epsilon into E plus or minus J omega mu J, all right? We then turn to our friend, the identity for the curl of E, and we get the gradient of the divergence of E minus Laplacian of E, and we have the same right-hand side. Very good. All right. You can also derive this wave equation, or no, sorry. The divergence of E is related to the charge density through Gauss's law. Divergence of D is equal to rho. So we can replace this divergence of E with rho over epsilon, right? You guys, okay, so let me write that. So because the divergence of D equals to rho, the divergence of E equals to rho over epsilon. What am I assuming when I make this equality about the medium? Homogeneous. I pulled the epsilon out of this derivative, so it's constant with respect to the variables that I'm differentiating over, which is x, y, and z. Okay, great. So we have the gradient of rho over epsilon minus del squared E omega squared mu epsilon E minus J omega mu J. All right. So let's move the terms to the left-hand side, or group terms that look like a wave equation, del squared E plus k squared E, right? So we have the wave equation on the left, but on the right-hand side, it's inhomogeneous. These are all driving terms now. So what I've done now is I've related, okay, so one more relation. We have the divergence of J is equal to minus J omega rho. So we can say rho is equal to, let me see how I mute these things. Where's mute? 1 second. Okay, everybody's muted. I don't know why. Oh no, let's see. There we go. Good. All right, so rho can be written as the divergence of J divided by minus J omega. All right, and then I replace that here. So now this is completely in terms of J on the right-hand side, right? So we've succeeded in deriving this first path here. What is E and H due to a current distribution of J or M? Well, here's an equation that gives me a E. I can solve for E given J, right? This is a very difficult differential equation to solve. It's a vector partial differential equation. It's inhomogeneous, and the right-hand side involves derivatives, right? And these derivatives are hard to handle. So, okay, so that's difficult to solve. Luckily, we don't have to solve that particular wave equation, right? That's what this whole point of taking this auxiliary path is. This is difficult to solve, but if we go this path and break it into 2 steps and derive a potential first, and then differentiate that potential to get the force, then it will be much easier to solve, right? So that's the idea. So let's look at the first approach. So now we're going to take the bottom path, right? Let us construct a mathematical vector field A. At this point, it has no physical meaning, although you can attribute a physical meaning of the potential due to 2 loops of current and so forth. So for now, and the way that Balanis approaches this is that it's a mathematical vector field A, a tool that we use to solve the problem. So this vector field A will relate to H as H equal to 1 over mu curl of A, right? We've seen this before. So we're defining that we get to pick this vector field. We're going to construct it. We're going to synthesize it, right? And we know from the Helmholtz theorem that every vector field is uniquely defined when we specify its divergence and its curl, right? We need to specify both. So first thing we're going to do is we're going to define its curl. The curl of A is equal to B. All right? This definition is not arbitrary, right? If we choose this, we can. We have to ensure that everything jives with Maxwell's equations, right? So we're going to make sure that it does. So here's a differentiation path, right? We get H directly from A. So here's A, here's H. We get H from A through a differentiation. All right? So H is 1 over mu curl of A. Good. So the force field is in terms of derivatives of its potentials. We need to ensure that A agrees with Maxwell's equations. So let's check them one by one. So this definition, where did it come from? It had some intelligence behind the choice because it satisfies first, then the magnetic Gauss law. The divergence of B is equal to 0. The divergence of the curl of A, because B is equal to the curl of A, is equal to 0 because the divergence of the curl of any vector field is equal to 0 by identity, right? So immediately we satisfy magnetic Gauss law. So let's check Faraday's law. Faraday's law is the curl of E equal to minus j omega mu H. We know what H is. So that's minus j omega, cancel the mu, curl of A. All right. We have a curl of A on the right-hand side and the curl of E on the left-hand side. Since this is a linear distributive operator, we can move the curl of A to the other side and factor out the operator. So we have the curl of E plus j omega A is equal to 0. Yeah? All right. We know that if the curl of some vector field, be it the summation of two vector fields, but that's another vector field, the curl of some vector field is equal to 0, then that vector field must be conservative, yeah? That means, because a conservative vector field has no curl, by definition. And also, a conservative vector field can be represented as the gradient of some scalar field. So we say that E plus j omega A is minus the gradient of phi. All right? Okay, let's see why we choose the minus sign shortly. All right, so then we can, from this equation, we can solve for E. E is equal to minus the gradient of phi minus j omega A. And you guys have seen this equation before. If I cover this part up, then we have E equals minus gradient of phi, right? You've seen that before in statics. So the electric field is the gradient of the scalar equipotential surfaces. You have normal, the vector field, E, the force field is normal to all of those equipotential surfaces, right? It's the gradient of the scalar potential. And that's why the minus sign is there. Because we know that the electric field decreases in strength as you go away from, say, a positive charge, and therefore it should point in the negative gradient direction. All right? Okay. But now we have this additional term, which is valid for dynamics. So E equals minus gradient of phi is only valid for statics. We now have this additional term, and this term is true in general. Because if we can reduce it to statics by saying omega is equal to 0. Omega equal to 0 is DC. That means this term goes away. We have E equal to negative gradient of phi. Good. So now when omega is not 0, we have the full form of E in terms of its potentials. Good. Okay. So this form of E satisfies Faraday's law, right? Because we derived it from Faraday's law. Let's check Ampere's law now. The curl of H is j omega epsilon E plus J. The curl of 1 over mu, curl of A, right? So we take H, we substitute in 1 over mu curl of A, and then we have j omega epsilon. We know what E is. All right, so let me remember, what do we have so far? We have H equals to 1 over mu curl of A, and we have E is equal to minus gradient of phi minus j omega A. I think it's plus. Let me just make sure. No, minus. Okay, minus j omega A. So here we have Ampere's law. We can substitute in for H and for E. So here's substitute in for H. Here's substitute in for E. And then we have, so you can multiply through by mu, and you get the curl of A on the left-hand side. You get minus omega squared mu epsilon into A, which you can move from the right-hand side to the left. And then on the right-hand side, we have minus j omega mu epsilon gradient of phi plus mu j. All right, good. So that equation up there was derived from Ampere's law. Okay, good. And it used the previous two results, which satisfied Gauss's magnetic law and Faraday's law. All right, so we're at this equation so far. Let's check electric Gauss law. So divergence of D is equal to rho. Divergence of epsilon E is equal to rho because D is epsilon E. We know what E is in terms of its potentials. Minus gradient of phi minus j omega A. That's all equal to rho. So then we can say minus, okay, so move the epsilon to the other side, divide both sides by it, minus gradient of the divergence of phi. And then we have the minus j omega A divergence of A. Yeah, minus j omega divergence of A. All right, this is nothing but the Laplacian, right? Divergence of the gradient minus j omega divergence of A. So we have another wave equation. This one's for A in terms of the charge, right? And the other one is A in terms of J. Almost. We're going to take care of that phi. But these two are related, right? So you don't have to solve them both. How are they related? One's in terms of current and the other's in terms of charge. How is current and charge related? Current and charge are related through the charge continuity equation. The divergence of J is equal to minus j omega rho, or negative partial rho partial t, right? So you can derive one from the other. Okay. All right, so Helmholtz decomposition theorem. Okay, this equation here is almost the wave equation that we want, right? But it has this extra phi in it. It's A in terms of J, but then there's phi. We have not chosen the divergence of A yet. Remember, we're synthesizing A. We chose the curl of A to equal to B. And we derived all these consequences from that choice. Now we still need to choose the divergence of A. And we're going to choose the divergence of A in a clever way such that we remove this term here. So if we choose the divergence of A now to be minus j omega mu epsilon phi, then the great simplification will happen to the above equations. So this choice is called the Lorentz gauge. All right, there are different choices. You could say divergence of A is equal to 0, but this choice is a common one, and we'll use this called Lorentz gauge. If you do that, so here's the four equations that we derived, right? This was the definition of A, the curl of A in terms of B. This is E in terms of its two potentials. We got this from Faraday's law. This is a wave equation that we're trying to solve for A in terms of J. But we have to get rid of this term that we derive from Ampere's law. And this we derive from electric Gauss's law, which is a wave equation for a scalar wave equation for phi in terms of rho. By using the Lorentz gauge, what happens? If we say that the divergence of A is, okay, so let's do this. All right, so the divergence of A is minus j omega mu epsilon into phi, which means that, okay, so there's some steps. Okay, so let's do it here. So the curl of A, right? What do we have to do with that? Let's change the color so that it stands out. So we're going to solve this, right? So the curl of A is, from our identity, we have, I think I wrote down, it's minus, okay, so it's the del squared of A minus the gradient of the divergence of A. I can't remember if I got these signs right. Let me check if we used it anywhere. Yeah, here. So it's the gradient, the Laplacian's minus. This one's minus, this one's plus. Okay. Minus, let's just call this K squared A. This is equal to minus J omega mu epsilon. The gradient of phi now, we're going to say phi from here is the divergence of A divided by minus J omega mu epsilon. So the divergence of A divided by minus J omega mu epsilon plus mu J, right? Now look what happens. This J omega mu epsilon cancels this J omega mu epsilon. And then we have the gradient of the divergence of A, but it is positive because this minus sign here canceled with this minus sign. So it's positive. When we throw it to the other side, we'll have minus the gradient of the divergence of A. This is plus the gradient of the divergence of A. So this cancels that. And then we end up with del squared A plus K squared A equals to minus mu J. And that we can solve easily. So here, del squared A plus K squared A equal to minus mu J. So you get this result from using the Lorentz gauge. You also can rewrite the gradient of phi in terms of the divergence of A divided by minus J omega mu epsilon. So then we have this E in terms of A only now. We have H in terms of A. All we have to do now is solve this differential equation for A given a J. Once we have that, we can go to these two equations and find E and H. This we don't need to solve because it's related to the current density, current distribution. Yeah? Questions? All right, good. So given J, if the solution for A can be obtained, then E and H can be found. All right, so we're trying to solve the inhomogeneous vector potential wave equation. If we compare the wave equation, we must solve for path one. What? If we compare the wave equation, we must solve for path one to that of path two. All right, so I think we must solve should not be there, yeah? So let me take that out of there. If we compare the wave equation for path one to that path two, we see why path two is preferred. All right. So path one, del squared E plus K squared E is gradient of the divergence of J plus J omega mu J. All right. So you don't know what's difficult about this yet, but when we try to solve this wave equation, we're going to solve for what's called a Green's function. And because of the linearity, we're going to solve for the right-hand side equal to a delta function. We're going to break our current density. We'll see that soon. But the preview, we're going to break the current density into a whole bunch of point sources that are weighted by the current density at that point, right? So then, because of linearity, I can find the radiation due to each one of these point sources, add them up at this point, and that's the same thing as the electric field at this point due to the whole current density because of linearity, right? If I take it, I'll show you. Well, we're going to see it next. All right. So, but the problem is I'd have to differentiate the delta function. That becomes problematic. The right on this one we can solve because it's much easier. The right-hand side is much, much easier, right? Good. So let's solve for the vector potential A by solving the inhomogeneous wave equation. Let's assume the source current density Jz, which is in the limit is an infinitesimal point source, is placed at the origin of a spherical coordinate system. All right. So, okay, what are we doing? We're solving this differential equation. We can't solve it for J. We don't even know J yet, right? It's arbitrarily defined. Some distribution, some density. It might be defined to us if we're trying to solve this for a given current density, but it might be a very complex function, right? And trying to solve this differential equation for this very complex input might be intractable, yeah? So instead, what we're going to do is we're going to say, well, I know by linearity, if I have some current distribution here, instead of solving for the field due to the whole thing at once, I can break it up into small, tiny, itty-bitty point sources. And I know how to solve for the radiation at some point due to a point source. And by linearity, by superposition of fields, I can add up the radiation due to all point sources. And I get the same result. So let's first solve this equation then for a point source. That we can do. That's a known source and it's simple. All right. So we place it at the origin of a spherical coordinate system. All right. So now we have del squared A plus omega squared A. We're assuming it's z-directed. It's a point source, but it's a directed point source. So this is current, right? It has to have vector nature to it. So you got to somehow imagine an infinitesimal point source that has spherical symmetry. So radiates equally in all directions, but it's a directed quantity, which is kind of hard. Okay, so it kind of goes against what you would know about current because in the direction of current, it doesn't radiate, right? We'll see that too. Anyway, it's a point source, but it has a direction. It's a directed point source. It's in the z direction, but it's a point source. So any point source, at any point removed from the source, so if we're not looking at the origin where this point source is, let me draw it. That might be a good idea. So we have, so here's z, x, y. There's some tiny point source here, but that point source has a direction, all right? It's not a dipole or an infinitesimal dipole because even an infinitesimal dipole has like a sine of theta pattern. Here we're trying to derive isotropic pattern, right? It doesn't exist. Isotropic pattern does not exist. You can never create an isotropic pattern because of exactly what I'm trying to say. Every current has a direction. All right. Anyway, so there's a point source at the origin. So at a point removed from the origin, we have this differential equation because J is 0. J is defined to be non-zero only at R equal to 0. At any other point, it's equal to 0. So del squared A, okay, so now we're assuming the source is effectively a point source. AZ is not a function of theta or phi because of this point source assumption. Hence, del squared AZ is a function of R now only. It's not a function of theta or phi, isotropic. It doesn't vary in angular, it's a sphere, right? A perfect sphere that radiates outward. Spherical wave. Point source. Plus beta squared AZ. What is del squared? Only the R component because it's only a function of R. So del squared, 1 over R squared, partial by partial R squared, partial AZ by partial R, yeah? Plus the beta squared AZ. All right? Okay. If you open up all these derivatives using the product rule, you can get this form here. Very nice. So this, the ODE here, so this is the ordinary differential equation because remember, these are only a function of R, so it's ordinary derivatives. This ordinary differential equation has these two solutions. E to the minus j beta R over R times C1. This is an outward traveling wave, or C2 times e to plus j beta R over R was an inward traveling wave. It's a second order differential equation. It has to have two linearly independent solutions. You can plug these into this differential equation and verify that they are solutions. What does this represent? It's only a function of R, which means that if I am the point source here, it's only a function of R, means that it only varies in radius. So if I go that way, or that way, or that way, or that way, it's all the same. It's an isotropic source. It doesn't depend on theta and phi. It's constant in those directions. So if it's a function of R only, it's a sphere, right? The phase depends only on the distance from the origin to the sphere, right? So it's an outward traveling wave. The phase delays in that direction, and it decays in amplitude as 1 over R. So imagine a sphere like a balloon blowing up, a perfectly spherical balloon, right? And then this one would be an inward traveling wave. So it travels toward the origin, it converges. That's the radiation due to a point source, right? Yes?
What about the other components of A, like Y or X?
Well, we assume that this source only is in the Z direction, right? We assume it's a directed point source at the origin, therefore it doesn't depend on theta or phi, but it has a direction and we chose Z. We'll see that it's the same for the other components. Okay, good. All right, so we want the outward traveling wave since it's the point source at the origin. To determine the coefficient, so there's an unknown coefficient, we use the following trick. We integrate the wave equation. So we have minus delta of R. Now we're gonna consider the point source at the origin, which is a delta function, right? In the limit over a small volume containing the source. So like this, here is X, Y, Z. Here is the point source at the origin. And we have some small volume surrounding that point source bounded by surface S naught of radius R naught. The volume is V naught. All right, so we take the wave equation and we are going to plug in our solution for A of Z, right? We know that this solution satisfies that differential equation. We're gonna integrate both sides over that volume now. And okay, so we have this setup, right? This is the dV in cylindrical coordinates from 0 to 2 pi in phi, 0 to pi in theta, 0 to R naught in R. Same thing with this integral. And this is the volumetric dV in spherical coordinates. And we integrate the delta function on the right-hand side over the same volume. All right, so let's work out the second term first, this one. So working out that term, we factor out the beta squared. Okay, it's there. And we start to do these integrations, right? So first off, there's nothing in this integrand that depends on phi. So let's integrate that one out immediately. So we get 2 pi from that, right? 2 pi beta squared C1 comes out. Now we have an R squared here and an R in the denominator. So we're gonna end up with R e to the minus j beta R. And we integrated out the theta. So now we have to integrate the sine of theta. Let's do the theta integration because that's the next easiest one. When we integrate sine of theta, we get what? Negative cosine. So negative is there. The integral from cosine of theta from 0 to pi is -2. So we get minus 4 pi beta squared C1. Now we just have to integrate the R dependence. To integrate the R dependence, we use a limiting process. So let's now let the limit, okay, so here is the result. We're going to take the limit as R naught approaches to the origin. All right. So what's the problem with integrating this? First off, okay, we're going to use a limiting process. So limit R naught goes to 0, right? Minus 4 pi beta squared C1. We can integrate this using the integration by parts. So if you integrate by parts, you end up with this result here, right? And we can now take the, okay, so first let's plug in the limits and then we can take the limit, right? So plug in the limits, then take the limit. All right, if you do that, then you get a result of 0, okay? Just trust me on that. All right, good. So the second term is 0. The third term on the right-hand side is -1. Why is it -1? This is the sampling property of the, or this definition of delta function. If you integrate any delta function, it's by definition, one of its properties is that you get 1. But this has a minus sign, so it's -1, right? Okay, good. So now we have the first term. The first term has a singularity in it. It has a singularity at the origin. So let's take a look at what that means. So del squared, what is del squared? Del squared is the divergence of the gradient, right? Let's take the gradient now and oh no, we're going to apply divergence theorem here, right? You remember divergence theorem? We can convert the divergence of some scalar function or the divergence of some function over a volume into a surface, a flux integral of the gradients of that vector field. Okay, so here, let me write down. Okay, so the integration over the volume of the divergence of, let's say, A dV is equal to the integration over the surface of A dotted with ds, yeah? Okay, so the divergence of this, right? So now it's this dotted with ds. So this is our A here. So this is our A, and we dot it now with ds, which is r hat. So it's a directed quantity, and it has this surface area, right? Okay, good. All right, so let's substitute in for the gradient. The gradient in r coordinate, a function that has r dependence only, is partial by partial r into this, right? In spherical coordinates. And then we have r hat. All right, good. The r hat dot r hat drops out, and we end up with the following. We end up with, so we take this derivative here using the quotient rule for this, and we end up with this integrand, r to the -2 minus rj beta, e to the minus j beta r minus e to the minus j beta r squared, all of this, yeah? All right, so C1 is still out front, and what have we done here? We've repeated, it's the same thing, right? Yeah, same thing. Why would I do that? The 2 pi, r to the -2. Okay, so yeah, it looks like I copied it. All right, so this line is the same as the previous, but anyway, you can now do the integration of theta. You get -2, right? Because the theta integration only has sine of theta. And then you can do the r integration, and you end up with this result. All right. Okay, good. Now we can take the limit as r goes to 0 to get the result for the third term. And what we find is we get -4 pi C1. All right, so let's combine all the results. First term, second, third term. This is the integral of the delta function. We got -1. The second term we know gave us 0. First term now gives us -4 pi C1. We can now solve for C1 as 1/4 pi. All right. Good. So the final solution to the inhomogeneous wave equation with a delta function on the right-hand side instead of j is e to the minus j beta r over 4 pi r. That is called the Green's function of free space for a point source at the origin, right? So good. So it's an outgoing perfect spherical wave. This result is called the Green's function and is akin to an impulse response from linear system theory. Do you guys remember linear systems, your course? Do you remember when you had a differential equation and you had some input, right? So you had some differential equation, linear time invariant. You had some x of t here, and you had some y of t outputs, right? But we couldn't solve this differential equation. Inside this box, there's a differential equation. We couldn't solve it directly for delta or for x, right, to get y, because the differential equation would be difficult to solve. So instead, we substituted in delta function. We fed a delta function into it, and we got h of t on the output. H of t we called the impulse response. And then how did we find the y of t from h of t? Well, we said y of t is equal to the integration of x of tau h of t minus tau d tau, right? And what did we call this integral? We call this convolution. And it allowed us to solve the differential equation which describes this linear time invariant system for an arbitrary input x of t to obtain y of t, but we did it through convolution. First, we solved for the impulse response, then we convolved the input function with the impulse response. We're going to do the exact same thing in electromagnetic theory because it's a linear differential equation. We're going to call our impulse response the Green's function. Instead of h of t, it's called the Green's function. So if the point source is not at the origin, then you just have to take care of the vector distance, right? You want it to be the vector distance. So say we have x, y, z. If the point source is here, so if the point source is here, then it radiates perfect spheres, right? If the point source is here, then it radiates spheres like that. And if we're observing over here, then you want the vector distance. So let me clean this up. X, Y, Z. If the point source is here, then you have one vector which points to the point source called the source coordinate, source position vector, and it is always primed. There's a prime. Then there's another point where you want to calculate the field at. That one has a position vector r, but it's unprimed. And all we care about is e to the minus j beta r over r, the distance from the source to the observation. From the source to the observation is this distance here. This is by minus r minus r prime. So that's all you have to do. If the source point is not at the origin, only thing that matters is the distance from the source to the observation point. In order to keep track of all of that, we have this new coordinate system or this convention where we have r prime pointing to the source, r pointing to the observation point, we subtract 2. And then we get the distance to the observation point from the source point. So let's look at the spatial convolution. All right. So here, remember Maxwell's equations and hence the wave equation are linear. And hence, we can treat this thing like a linear time invariant, right? So del squared A of z plus beta squared A of z. This is the differential equation which describes our system. Our system is free space, radiation due to a point source, right? That's what this differential equation describes. We cannot solve this directly for a j, right? So what we're going to do is break the j into, so here's j, some blob of current, right? This blob is a function of r prime. R prime is a vector that points to different points, right? So this is r prime, or r prime could be here, but the current density is a function of r prime is x prime, y prime, z prime, right? It's a vector. So this distribution has all points r prime, and it's a vector. So at each point in this distribution, it has a vector, and it has a complex amplitude, magnitude and phase. The source point is P, right? What is the vector potential at P due to the source distribution J? Well, we have to solve this differential equation to figure that out, right? All right. But we can't solve it for this whole blob at once because that's a very hard differential equation to solve. So we're going to solve by linearity. What is linearity? It says alpha. So linearity means, alpha x1 plus beta x2 is equal to alpha y1 plus beta y2, right? The coefficients, they go right through the system, and they also multiply the outputs by linearity, right? That's the definition of it. And I can take a sum of two inputs, and I can just sum the two outputs, right? Okay, good. So, okay, so what I'm saying here is I could feed this differential equation here, delta 1, scale it by alpha 1 first, and I get AZ, so delta 1 at R1 prime, so 1 point, and I scale it by the same alpha. Then I can feed it delta 2 at R2 prime, a different point, scale it with a different coefficient, and I can just add that to the output. So if this current distribution here, I can break into a bunch of delta functions here, and each of these points here, the alpha comes from the current distribution at that point. That's the scaling of the delta function. So if I break this into a bunch of delta functions, or point sources, or delta functions, and at each of those point sources, I scale that point source by the current density at that point, then I've discretized this current density into a bunch of weighted point sources, right? And then I feed each one of those into the system one at a time, and I add up their outputs. All right, good. So what am I saying? I take this current distribution here, and I break it into a bunch of point sources, right? Each one of these grid boxes, I put a delta function in there. But the delta function, if I did that everywhere, then I would just have uniform unit amplitude currents everywhere, right? Just be one angle 0 everywhere. And it would have no direction. What I do is I take that delta function, I weight it by the current density at that point. So now it's an inhomogeneous distribution. It represents the actual current density, but broken into point sources, and it has the direction of the current at that point. All right, so we can weight the outgoing spherical wave, the Green's function. We know what the solution is to each of these point sources, right? We know these AZs. These are the e to the minus j by r 4 pi r. We solved this differential equation for the point source. Now we just add up a bunch of e to the minus jkr over 4 pi r's together with these different weighting coefficients taken from the current distribution, and I sum all those up at point P. And I get the radiation due to that current distribution. Pretty freaking cool. So, okay, due to each point source in the current density distribution by the current density at that point, and add up each spherical wave emanating from each weighted point source at the observation point to get the total vector potential, right? By linearity, I can add them all up. This process of adding all these up, breaking it up and then adding them all up. Let me see if there's any more animations here. Yeah, so I point to R prime, right? Some distribution. That radiates like a spherical wave because we know the solution to a delta function. I point to the observation point with R. So the source points are always R prime. The observation is always unprimed, or R. I subtract the two. I get capital vector R, which is the vector of interest. That's the only thing that matters. This radiates like a spherical wave with this local coordinate origin up to the observation point. Only thing that matters is distance from the source of observation. So it matters that R, capital R, right? Okay, so what matters is that capital R. So I can do that for this, I can do that for this point. So this little point source radiates like a sphere to this point. I get some number, right? Then I might point to this point. This one radiates a spherical wave with a different weighting coefficient, alpha maybe, and I add up its points. So I have this vector from the first one, that vector from the second one, so forth. I add them all up, and I get the total field there. Okay, this process of breaking it up and adding it all up, breaking this into a bunch of point sources that are weighted by the current density, adding up the radiation of these point sources as a spherical wave to that point and adding up all of it, that superposition process is called spatial convolution. It's a convolution integral. That's what it is. I'm sweeping some kernel over this current density. That kernel is the Green's function, the point source. And for each pixel of this, say, current density image, I'm sweeping this kernel over that whole current density by sweeping this R vector to each point. So R vector sweeps to each point, and I take that kernel, which is this e to the minus j beta r, weighted by the alpha. So the current density at the point R prime gives me the alpha for that point source. I multiply it, I weight my e to the minus j beta r over R by it, and that becomes a radiation due to the point source that's weighted with the current density at that point at the given R prime. Then by integrating, I'm integrating over prime coordinates, which means I'm sweeping R prime. I go to the next point source and I weight the e to the minus j beta r with the new R, right? Big R changes, and I add that up. This whole thing of adding all that up is called spatial convolution. Yeah? Yes.
So the point is always outside the current region.
No.
Point B,
No.
the inside,
It could be. If it is, what's the problem there?
so the singularity.
Very good. R goes to infinity. R goes zero, then it blows up, right? So there's a process called method of moments where we want to calculate what this current density is accurately. Sometimes we're assuming we're given this current, right? But if we haven't been given it, we can calculate it using a boundary condition and a known excitation, for example, using the process of method of moments, a numerical approach. We'll learn that next semester if you take the next course. But in that sense, we have to treat the singularity. And that's like the hardest part of all of that numerical algorithm is taking care of the singularities. But it's doable. But yeah, good observation. Okay, so here we've done it. We've now given the current density, we've calculated A to an integration, right? We already know once we have A, how to find E and H by differentiation. Good. So since AZ is directly related to JZ, we can also write, okay, so this is a linear relationship, right? There's no curl or anything mixing these components. So Z, this is the only vector component. Well, Z component here comes from Z of current. So that means A is in the same direction as J all the time, right? These are both vectors in general. Down here, they're both vectors, but A is always in the same direction as J. All right, so this is the integral we got to solve. So let's go back. Let's go back to here. Remember, we needed to find A in terms of J, and we have now done that, right? A in terms of J is A at some observation point R is mu integration. I think 4 pi came out, right? J R prime e to the J beta capital R over R dV prime. Yeah? Should be minus. Yeah? So we start with current density, we're given it. Then we calculate A using this integration, this convolution. This is over a volume, by the way. Put the volume here. Then once we have A, we just differentiate it, take the curl or the divergence and so forth to find H. And then once you have either E or H, you can easily find the other through Maxwell equations. Good, 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 good. Okay, let's do an example. Dipole. So let's see how to calculate A. So we have a dipole here at the origin, right? This dipole has some length delta Z, and there's some observation point P, and it's a Z-directed dipole. This is an important result. We're going to use this throughout the course. So we're going to derive it here and remember it. So A is equal to mu integration over volume, J e to the minus J pi R over 4 pi R dV prime. We already derived that, right? Now, let's add the integration of the volume. So we're going to integrate over, okay, this current density, have I written it down? Okay, here it is. It's Z-directed, it has some current in that direction, it has some length, delta Z, but in the X and Y direction, it has no length. So delta function in X, delta function in Y, right? And then we can integrate over volume, minus infinity, plus infinity. We're integrating delta functions in those directions anyway. And we're integrating over the Z direction, all right? So I comes out, it's a constant, the unit vector comes out. Why does the unit vector come out? Very good. You did that in your first homework. The unit vectors could depend on position. If it was a spherical coordinates or cylindrical, that might not happen, right? You might have to integrate. Okay. If it depends on the integration variables. E to minus J bar 4 pi R dZ prime, right? All right, so look at this geometry. We're assuming that this point here is much farther away than the length of this. We're assuming it's very, very small, infinitesimal, right? So if you do that, then since delta Z is much less than the lambda, this is lambda by 50, for example, and therefore R, if this is very small, then this R from the origin to the observation point and R from the top of the dipole to the observation point are nearly the same because the dipole is lambda by 50 tall. This has to be drawn this way so you can see the difference. but imagine this almost being a point at the origin, right? If it was a point at the origin, then the two R and R, capital R, little r would be the same. All right, so we can make that approximation. Therefore, we can replace big R with little r. So e to the minus j beta r over 4 pi r mu I delta z. If you do that, then this does not depend on z, right? It's r. So we factored that out, and we're just integrating delta dz from minus delta z over 2 to delta z over 2. We get delta z. So here's A. This is exactly true for a point dipole, as we said, because big R and little r are the same, and approximately true for uniform current, for small uniform current elements. If any of these conditions does not hold, then the substitution of R, approximately R for the phase term is not valid. Okay. We can calculate the fields now that we have A. H is equal to 1 over mu curl of A. So we take the curl of this expression. 1 over mu, the curl of z into z hat, right? It only has a z component. And we're going to use this identity. The curl of a scalar function multiplied by a vector function is the gradient of the scalar crossed with f plus the scalar times the curl of f. If you do that, then you end up 1 over mu, gradient of az, right? Gradient of the scalar function crossed with z, the vector component is z, plus 1 over mu, the scalar component is az, curl of f, which is z hat, right? All right, good. The curl of a constant vector is 0. Z hat is constant, right? A constant vector field, you can imagine everywhere in space. So z hat is vertical, right? So no matter what point I pick in all of space, z hat's always in the same direction. That vector field is the prime example of one with no curl. It's always going the same direction. It never curls, never circulates. So that means this is 0. So then we end up with 1 over mu gradient of A crossed with Z. That helps us because it's easier to take the gradient of that than the curl of it. All right. Taking the gradient in spherical coordinates, we have the gradient of this expression, which we calculated here. We have I delta Z over 4 pi. We have the derivative with respect to R because it only has an R component for the gradient. We have to differentiate e to the minus j beta r over R. And then we have the R hat comes from the gradient crossed with Z. So we end up with I delta Z over 4 pi, quotient rule on this guy, we get these two terms. R crossed with Z is nothing but sine of theta. R crossed with Z. Remember why? Okay, R crossed with Z. R hat crossed with Z hat. Magnitude of R, magnitude of Z, and sine of theta, sine of the angle between them. So the angle between Z hat and R hat is theta. But that only gives you the magnitude, right? What's the direction? Well, if you think about it, if I have Z like this, Z, is it R cross with Z? Yeah. Start with R, then you cross with Z, you get phi. No matter where this R is. So let's say R sticking out of the board now. So I have R crossed with Z, I get phi, right? You get negative phi. Is it negative phi? R crossed with Z. So let's say R is in the XZ plane, right? The XZ plane. We know phi is pointing along the Y direction. So if R is in the XZ plane, so yeah, and Z should give you negative phi, yeah? R cross with Z gives you negative phi hat sine of theta. Yeah, here, look. These minus signs, we factor, yeah, these minus signs are gone now, yeah? Minus phi hat. So R cross with Z gives you minus phi hat times sine of theta. All right, so this is the result now for H. What time is it? Okay, good. All right, any questions? So we found H now. Now we're gonna find E. We just go, once we have one of the fields, we can find the other by using either Ampere or Faraday's law. So we're gonna use the Ampere law here. Take the curl of our H result we had before, divide by j omega epsilon, we get E. So if we do that, this is the result, okay?
And we can write them in a more simple form in these two. So this is the final result that I want to discuss. We have H, we have E. This is a very important result to understand. First off, H has only phi component. So the current is like this, right? Thumb in the direction of current, Z, and the magnetic field curls around it. So if my thumb is the direction of current to Z, then what curls around Z is phi. So the magnetic field only has phi component. All right. The other thing is the magnetic field has 1 over R and 1 over R squared. Remember those are important. 1 over R and 1 over R squared. The electric field here has theta and R. All right. Has theta component and R component. And it has 1 over R, 1 over R squared, and 1 over R cubed for the theta. And for the R component, it only has 1 over R squared and 1 over R cubed. All right. Okay, so if we want to observe in the far field of this infinitesimal dipole, then we know that all the 1 over R cubed and 1 over R squared terms are going to die off, right? We're only left with 1 over R terms. So in the far field, we'll have just I delta Z 4 pi J beta, E to the minus J beta, R over R sine theta, all right? And in the far field for E, these R term is going to drop off. We expect that because in the far field, there's no radial components, only transverse components, right? Theta and phi. All right. This is one way to understand that. Then we'll have this term and this, right? These two terms will go away. If you divide these two, you get eta, which we should expect. Locally plane waves by stationary phase. Okay, so let's look at different regions that we can analyze this at. So there are different regions. We have, if we have a small antenna where A is much less than lambda, like the one we just analyzed, then we can break the radiation into multiple regions. The first one is called the reactive near field. So in this region, if you compare this electric field here, this form here, to that of the scalar potential, V, due to a dipole of charge, you will find the exact same expression if you keep only the R term, R cubed. All right? So it is, the near field is the near field of a dipole charge. Okay? That radius, that where those fields dominate, the reactive fields dominate, is lambda over 2 pi, called the radiant sphere. Then the fields start to radiate, right? So here we have a bigger antenna, for example. The reactive near field is very near the antenna. Then the pattern looks very kind of uniform. It's an aperture, right? It's an aperture field. Then you move away from the antenna a little bit. You get into what's called the Fresnel region, where the pattern starts to develop. Interference starts to take hold. We're starting to see transverse components only. The R component is starting to die out. And for small antennas, that is called the radiating near field, up to about 5 lambda. For bigger antennas, that's called the radiating near field. And the distance is from this quantity, 0.62 squared of D squared over lambda, or D cubed, I can't read that, to 2D squared over lambda. 2D squared over lambda is the far field distance. All right? In this region, the pattern's starting to develop. The nulls are starting to appear. Interference is taking over. The R component is starting to decay. But it's still a function of R, right? It's still a function of R, the pattern. We'll see more about this later, all right? In the far field, when you get past 2D squared over lambda for a big antenna, or past 5 lambda for a small antenna, you end up in what's called the far field. And the far field, we only have 1 over R terms. What's unique about the far field is this pattern here, this angular dependence, this is a function of theta and phi here, this radiation pattern. It's formed and it's not going to change anymore with distance. No matter how far you go away from the antenna, past the 2D squared over lambda out to infinity, this is the same radiation pattern. It'll decay in amplitude and change phase at each point, but the shape of this pattern will not change. So this becomes independent of R. All right, good. Okay. So electric scale. Okay, so we could do all this. We did all this for A, J, and H and E, right? You can get both of them. But now we're gonna look at what if we have magnetic current? And if we have magnetic current, we're gonna do the exact same thing. We're gonna calculate F instead. So nothing new here to learn, except we're going to repeat what we did, except we're gonna change the source. And you'll see later why this concept of duality, you'll see all of these things are very dual, right? You just change one variable, epsilon to mu, E to H, H to negative E, and so forth. So anyhow, we're gonna define an electric vector potential now instead of a magnetic vector potential. It's going to be F, and we're gonna define it as the curl of, or D, negative D. So D, so here D is equal to negative the curl of F. Before we had B equals the curl of A. All right, so D is equal to negative the curl of F, all right? Do the same thing. That satisfy all these differential equations. Why do we choose this definition? Because if you go to the electric Gauss law, the divergence of D is equal to 0. Here's our definition for D. We take the divergence equal to 0. That is satisfied because the divergence of any curl is equal to 0. And Pierre's law, we do the same thing. Curl of H, J omega epsilon E. Now, this E is equal to minus the curl of F. So minus J omega curl of F. We have curl on this side, curl on this side. Move this term to the other side. The curl of H plus J omega F equal to 0. Curl of any vector field that's equal to 0. This vector field can be the gradient of another scalar field. We call this the magnetic scalar potential. So this is kind of a fictitious quantity. H plus J omega F is minus gradient of M, gradient of phi M. H in terms of its potentials, minus gradient of phi M minus J omega F. Exactly analogous to the electric current case. All right. And we can do the same thing for Faraday's law. We end up with, this differential equation, the curl of F, in terms of phi M and epsilon M, right? So now this is F in terms of M, right? F in terms of M, we got to get rid of this term. We're going to use the Lorentz gauge again. And by using the Lorentz gauge, we end up with this wave equation that we have to solve now, but it's the exact same form, right? We already solved it. We already know if we replace this M with a delta function on the right-hand side, what the solution to this differential equation is. Still a radiating point source, right? Or a spherical wave. Okay, let me just check where we're at here. Okay, good. So, yeah. Okay, so, and then we can go to magnetic Gauss law and we get the analogous equation for rho, the magnetic charge density, if it existed, in terms of its potential, right? All right, good. So given an M, if a solution for F can be found, we can find E and H, right? Some problems have J and M, so you have to use both these apparatus to find your E and H. All right, good. Any questions? All right. You guys are moving around in your chairs and stuff. Is it too much or what? All right. All right. If both J and M are present, here's a flow chart, all right? So here's our flow chart. We have sources J and M. Instead of going the direct path to find E and H, which was difficult, we're gonna take this auxiliary path where we calculate this auxiliary vector potential, magnetic vector potential A, electric vector potential F in terms of J and M. Then we can differentiate those to find E and H. So A is given by the spatial convolution. We solved that. F is exactly the same, except now we have epsilon over 4 pi and we're integrating the magnetic current, right? Same thing. Then E now has some contribution due to the electric current and some contribution due to the magnetic current. So you have to sum them up. And you can use this formula. There's A and F here and A and F here. So you can, if you have both currents, then you use this approach, all right? So the result for J alone or M alone can be obtained by setting either M equal to 0 or J equal to 0 in the expressions above, all right? Good. Let me just see where we're going here. All right. Well, we still got some time, so let's do it. So, all right, so we want to find, that was radiation in general, anywhere. Point P was restricted to be in any region, right? It could have been in the current distribution itself. It could be near the current distribution, in the radiating near field, reactive near field, or the far field, right? But now we want to specialize the result because that calculation is difficult to do, the integration. Because that, okay, so this calculation, it's not impossible, of course, but this R changes. This R is a function of the source coordinates, right? Capital R is, remember, capital R is, so if we have some J here, some P here, then we point to some point here with R prime, right? We point to the source point or observation point with R, and then we calculate this vector, which is capital R, which was R minus R prime, right? Now, when you're integrating over the primed coordinates, which means you're integrating over this whole blob here, then this R changes. So the integrand is constantly changing. So it's not like you're integrating cosine of theta or, x squared plus sine theta or something. The integrand is changing all the time. I guess, okay, so it's parameterized in terms of variable, but it's a difficult integration to do, right? A lot of times you do this numerically. But if you want to find the near field. But we can simplify this integrand such that it's no longer a function of, I mean, it's still a function of the source coordinates, but only in, it's a much simpler form that you can handle by assuming we're looking in the far field. For far field observations, if P is in the far field, then this becomes much easier to solve, all right? So let's take a look at that. A general solution to del squared A plus omega squared mu epsilon A equal to minus mu J, which is our inhomogeneous differential equation, in spherical coordinates can be expressed in the following. We have R, theta, and phi components. And each of these terms contain some 1 over R to the n amplitude variation, all right? We saw that with the dipole, right? So they have 1 over R squared, 1 over R cubed, and 1 over R, right? So there is different types of amplitude variations in each of these components in general. All right. In the far field, we ignore radial amplitude variations in the R direction of order higher than 1 over R. All right. So anything greater than 1 over R, we ignore, because if we have 1 over R squared, 1 over R cubed, and 1 over R, then if we go out to infinity, 1 over R cubed is 0. 1 over R squared is 0. And 1 over R is pretty small too, but we keep it, right? So we have to have some fields out there. So 1 over R dominates over 1 over R cubed and 1 over R squared and 1 over R cubed. All right? So we only keep 1 over R. So A then can be approximated in the far field as R hat, we call it AR prime because it's different than AR, a function of theta and phi only because we factored out this R dependence out here. And we have theta and phi, all right, as R goes to infinity. Okay, so if we plug this approximation into the expression for the electric field, for example, minus J omega A minus J 1 over omega mu epsilon gradient to the divergence, that results, if you do that and you plug this in here after done with the pencil shavings and all of that, you'll get this result. E far field is minus J omega A. So let's do it. All right. So I didn't just say this left to the reader. We're going to do this. Okay. All right. So let's work it out. Let's work out first the divergence of A term. So this is the result we're after. We're going to prove. Okay. So we're going to plug this A into this divergence operation. All right. So I remember doing all this for you guys. So here's A. Divergence of A. Well, we have R, theta, and we have phi. This is the divergence definition in spherical coordinates. All right. Well, let's do this R derivative here so we can take the derivative of this. And we end up with this expression. Take the theta derivative here with this, open it up with the product rule, and then we have just a regular phi derivative. Yeah, so look at here. So here, let's do this one. We have r squared multiplied by ar. Well, here's ar plus that part, right? So r squared multiplied that becomes r e to the minus j beta r. And then we have to differentiate that with respect to r. So if you do that, then you can use the product rule and you get, oh, we haven't even done it yet. Here's er, that's r squared multiplied by ar, right? We still haven't done the derivative. Then a theta, we have sine of theta multiplied by a theta. Well, a theta is this plus the e to the minus j beta r. So there's sine theta, a theta that. We still have to differentiate. A phi is nothing but this. So here's a phi. And then we differentiate with respect to phi. All right? All right. So what are we doing here? So we didn't do anything in this line, right? That term's the same. That term's the same, all the same. All right. So now you use the product rule here. Remember, this is an r derivative, but this is not a function of r. So that comes out. And we just do the ordinary product rule there. Then we have differentiation with respect to theta. So we haven't done that one yet. And we have differentiation with respect to phi, but this e to the minus j beta r does not depend on phi, so we pull that out. All right. So keep this result in the back of your mind. Now we take the gradient of this result, because we need the gradient of the divergence. Okay, so gradient of all of this, I repeated the result, added the gradient. And here is the gradient vector in spherical coordinates. And this is repeated. All right, and this is repeated again, no change here, right? So this is another result. Oops. Okay, so repeat it again here. So now you got to distribute all of these vectors into, okay, so this is a scalar, right? This whole thing is a scalar, it's not a vector. So we have to distribute that whole thing into here, and into here. So first one, we do this with respect to r, differentiate this whole thing with respect to r. We get this term here, and we call that the r hat term. Then we do the theta and the phi, but distributing it to here and to here. So the details are here. I've gone through all of this. All right, so you end up with this big old result here, right? R, theta, and phi components. Now you add the minus j omega a, and here's E, minus j omega a plus this coefficient. If you do that, so we have the minus j omega a, we have the repeated result with the r, theta, and phi here. If you do all of that, then you get this expression, all right? So now, it's repeated here. Now, we want to concentrate on only the 1 over r term. So what we can do is go through this and cancel out everything that is higher than 1 over r. What we get is, this is minus j omega, this has a 1 over r only, right? That has 1 over r, so we keep that. So there's here, right? Okay, now, let's look here. This has r, it has r cubed, so the r cubed will be irrelevant. So we have, I think that's this term. And then here we have r squared, this whole term goes away. Here we have r squared and r cubed, this whole term goes away. R squared, that whole term goes away. We have an r here and an r here, this whole term goes away. That goes away. R squared, this whole thing goes away. R, that goes away. R, that goes away. So only thing we kept was this and the first term of this one, right? We have this piece and that piece. All right, good. So that's here and here. Good. Now, plus we have these higher order terms that we said goes away, right? But we can just say that they're r squared, r cubed dependence. All right, so contribution to r hat component to the far field in second term cancels that in the first term. All right, so yeah, okay, look here. So this is the key result here. This is what matters. We have an r here, minus j omega r hat ar, plus j omega r hat ar, e to the minus j beta r, e to the minus j beta r. So this term cancels that term, right? And all we have left is theta and phi dependence in the far field that decays 1 over r. So we have theta, phi that decays 1 over r only. So only transverse components in the far field that decay is 1 over r. I just stated that earlier, but now we've proved it. In the far field, there are no radial components, only transverse components, theta and phi. And they decay as 1 over r. That's all that there is in the far field. Therefore, in the far field, we can say that E far field is minus j omega a. We keep only keeping only transverse components. And H is minus j omega f. All right? That's a super good result. That means that this result here, this part goes away in the far field. So you can calculate far field E from A just doing minus j omega times the A. You don't have to do anything after you calculate A. You just multiply by minus j omega, throw out the real radial component. R hat goes away. A might have R, theta, and phi. Ignore the R. Keep only theta and phi, multiply by j omega and minus, and you get your E. All right, so we'll continue from here next time. All right? Very good. So make sure you start your homework. It's coming out today. All right, so you'll have a new homework today. All right, and let me know if you have any questions. I have office hours today. All right, guys. Oh, here, come get your exams and your homeworks. They're up here. So let me separate these in terms of midterm, and I think this is homework. So here's midterms, and then here's homeworks. If you're here, come get them. And if you're an online student and you want these physical copies, email me. I'll scan them and send them to you, to your email. All right, thank you. Sure.
The group potential from this distribution. So just consider it as a linear time invariant. What about time variant?
Time varying sources.
Can we do this combination on time too? Like a spatial convention? And then add them up? I don't think.
I think you, okay, so if you can represent your time variation in terms of the superposition of like temporal harmonics, then maybe for each harmonic you could apply this approach. So, okay, yeah, I haven't done too much work in temporal stuff, yeah, but I'm sure there's a way to do it. But I would assume that you'd have to modify this, of course, this theory. And what I have seen in terms of people working on temporal stuff is sometimes you can expand the temporal distribution in terms of temporal harmonics, time dependence in terms of harmonics. And then for each of those harmonics, you can use linear theory.
So it means that in like two space, we have that combination.
Yeah, because if you can expand the time dependence into harmonics, then you have time harmonic theory again, right? For each of the harmonics, because you have one frequency excitation of each of the harmonics. Say you have some kind of triangle wave for your time variation, do a Fourier series on that. Then you have a bunch of single frequency contributions to that, to the time dependence. Maybe you could do something like that. Yeah, very good. Good job on the exam too.
Yeah, that's, I can, yeah. This book.
You sure?
Yeah.
Well, you gotta fix that. Okay, that's pretty sure. Oh, we'll fix it.